All right, well today we are going to talk about the next GD&T symbol, which is going to be position. So the position, as we'll see, is just another way to locate things aside from just using regular old linear dimensions, and will allow us to have a little bit of a different variance. We'll see that in just a few minutes. So the position symbol you can see is there, and typically we'll be applying this to features of size, typically cylinders and holes, and we'll be locating them relative to other datums. So we'll be calling out datums on these as well. This particular one has a circular shape, kind of like when we were calling out the straightness of an axis. So we'll be using the diameter symbol for the position as well. And talk about some of the symbols again as we go through here. You can use the MMC or the LMC, or remember, if you don't put anything, it's regardless of feature size. And then we have to use basic dimensions to call out the features. I'll show that in just a few minutes. But let's talk about the tolerance zones themselves. So thus far we've been doing coordinate dimensioning, and essentially that gives us a rectangular tolerance zone. So if I'm calling out where the center of this circular feature is, I've got a tolerance of 5 thousandths here, so that gives me a tolerance zone this direction of 5 thousandths, and then same thing vertically. So the center of that axis can fit anywhere within that square. Or in this case, it's a rectangular one. But that's essentially what we're saying when we are calling out a shape based on linear dimensions. Now, if I take a look at what that actually means in any given direction, if I were to think about where the center of this axis would be, I'm basically saying that it could vary up and down by 0.0025 each direction, right? So a total variance of 5 thousandths. But if you think of the diagonals, it's actually allowed to vary even further. It's allowed to vary 7 thousandths and some change. So does that make sense what I'm saying there? So just looking at the axis itself and which direction it's going, we kind of have a different allowable variance when you're dealing with a square shape or a rectangular shape. So when we're doing the location tolerancing, then, or position I should say, then we can actually use this larger tolerance zone. So we can use the 7 thousandths instead of the 5 thousandths, which gives us a little more breathing room and gives us more possibly more parts that are in the allowable zone. So, bringing in the old Pythagorean theorem. So if I want to figure out what the tolerance zone is, then we've got to basically treat it like a triangle, and I'm trying to figure out the hypotenuse here. So it's a squared plus b squared equals c squared. So that's where we get 0.005 squared plus 0.005 squared. And then the square root of that would give me the hypotenuse. So if it's been a while since you've done that, I can help you out when you get there and step you through it. But that is going to give us the actual tolerance zone that we can apply to our position tolerance. So looking at this example, if I were to just use the linear dimensions, I've only got 3 good parts here. A, B, and E that actually fit inside the square. But if I go ahead and apply the tolerance to it, I've got 3 more good parts that fall within that range. Again, they all vary no more than the 0.007. And so they're all good parts. Oops. Okay, so again, this particular case, we're just looking at the tolerance values to figure out what the tolerance zones are. So this particular one's a square tolerance zone with 4 thousandths in each direction. And then to figure out what the positional tolerance is, then we're going to use the Pythagorean theorem again. So 4 thousandths squared plus 4 thousandths squared equals that. Take the square root of that, and then you've got 6 thousandths. So 6 thousandths is our diameter tolerance zone, and that's what we would put into our control frame. So again, another example here. We've got 2 different tolerance zones, so it's rectangular, but I can still find the hypotenuse to find the 11 thousandths there. So you'll be asked to do a little bit of Pythagorean theorem and figure out what a tolerance zone is going to be. But let's take a look at just a simple drawing. So up until this point, this is things that we've done. So I've got some location dimensions to locate these holes. Now I didn't dimension the overall shape, but just focusing on the holes. So this is how we've called things out so far. I can find the center of this one because it's 0.875 over and 0.625 up. This one's 0.875 over and then another 1.75 up to here. So we've properly called out where those two shapes are, called out the size of this particular hole with a tolerance, and then indicated that it's datum C, indicated that the right side of this part is datum B, and then the back side of this part is datum A. So notice first of all that as I'm dimensioning this 0.875, I didn't come from the left side, I come from the right side because the right side is the datum. So that's one thing that you want to make sure of, is that you're dimensioning from the datum. Okay, so that's old method. So what if I want to go ahead and apply this tolerance to it? So here is the size of this hole. Diameter 0.75 plus or minus 2 thousandths. And I'm told that we have a 4 thousandths diameter tolerance zone. So you can see that represented in green, actually blown up because you'd barely be able to see it if it was full scale. And it says it's at MMC, and it tells me that it's relative to datums A, B, and C. So how's it relative to A? Well, because it's basically perpendicular to plane A. So a lot of times you'll see these locations calling out the plane that it's going to be perpendicular to as well. So it's going to be perpendicular to this plane, and then it's relative to B, and then it's relative to C here. So that's why the dimensioning is called out here. A baseline dimension wouldn't have made sense because this is going to be datum C. So I'm going to call that out from there. Now, like we talked about when we were doing angularity, I want to make sure that my tolerance for the location of this shape comes only from here. I don't want to apply any tolerance to the location dimensions. So we need to make sure those are basic dimensions to call those out. This one doesn't have to be basic because it can use the title block tolerance to locate this one. But once this one's been located, then we want to make sure that we use a basic dimension because the tolerancing for the location is going to come from the position tolerance up here. So a few more examples, just one hole called out. Again, here's the tolerance, the size of the circular control frame, and then we've got it relative to 3 datums in this particular case, and again, basic dimensions. So here's a couple of holes, and again, notice that on the dimensioning that I'm coming off of the datums. So I didn't measure off the bottom to where this one's at, even though, a lot of times in dimensioning we would say, well, it's closer to the bottom, so it would make a cleaner dimension to locate it from this bottom or from the right side. But because I've got datum B up top and datum C on the left side, I need to make sure all my dimensions come from those datums. And then again, we've got it relative to datums A, B, and C, A being just perpendicular to that plane. A little more complex one. Let's hop over that one. Take a look at this one. It has, again, a few positional tolerances in it. So for example, this particular hole is saying that it's a tolerance zone of 1/10, and it is relative to datum C. So datum C in this case is actually the left side of the part. So there we have a basic dimension calling it out from the left side of the part. And then we have it relative to datum F, and datum F is actually this hole. So it's the center of this hole, so basically they're the same, they should line up. And then finally datum A. So datum A, it looks like, is the bottom of the part. So here is the dimension that calls out the center from the bottom of the part using the basic dimension there. So the plan then are 3 drawings from the Chapter 9 folder. Pop into them and show you what you'll need to do on those. Maybe. Okay, so templates folder, GDT folder, and then the 16-9 folder. The first one, you are to just give me some tolerance zones. So part A, we've got plus or minus 100th. So what would the size and shape of this tolerance zone be? And then the second one is, as you can see, two different values. So the shape will be a little different. It won't be a square. And then what are the sizes? So for example, a 6x9 rectangle or a 6x6 square is what I'm looking on those. And I'm just making up values, but so the size and the shape. And these are little tables. You can double click on them and then type in your answers in there. And then what is the distance of the extreme permissible position of the hole? So that's where you're going to use your Pythagorean theorem. So if it's 0.05 by 0.05, then you're going to square those, add them together, and find the square root. And again, if you need help, if it's been a while since you did the Pythagorean theorem, let me know. But then that resulting value would be what we would put into the tolerance, or the positional tolerance. But we won't actually add that in here. We're just going to find the value. Does it make sense what you're looking for on the first one? Okay. On the second one, okay, so on the second one, you are given some instructions up top here. It says the 4 small holes are to be located within a diameter tolerance zone of 0.25 at mmc relative to the axis of the large hole in the center of the part. And datums A and B. You must establish the datum for the large hole. So if we go on to number 2, it says the large hole is to be located relative to datums A, B, and C, and within a diameter tolerance zone of 0.25. So I'm actually going to work backwards on this one. So datums A, B, and C, you can see which planes are A, B, and C. So call those out as datums, and then you can delete the text there. And then the hole D is located relative to A, B, and C. So that means I want to dimension off of B and off of C with some basic dimensions, right? Because we have a location. And then that is going to be your other datum. So you'll probably call it datum D. So hang the datum D off of that control frame so that in line 1, when it says the 4 small holes are located within a diameter tolerance zone of 0.25 relative to the axis of the large hole, that means you should be dimensioning off of the large hole. So for example, oh, you got to do it inside the viewport since it's a metric one, forgot. So there to there, for example. And then it's going to need to be basic. So I'll go to properties in case you've forgotten how to do that. And come down to tolerance display and set it to basic. And then when I call out the tolerance, then I'm going to make it relative to datum D. So whatever this hole is, as I dimension it, and then I add the control frame underneath it, then I'll also call it datum D so that I can reference datum D in these other holes. And then fully dimension it. Which really, the only thing left to dimension should just be the thickness of the rectangular shape, because you should have dimensioned the location of all the holes before that. All right. And you can do a 4 times on your hole callout, including the control frame. So you don't have to do it for each individual hole. You can have 4 times diameter of whatever it's going to be, and then add the control frame underneath it to apply it to all 4. So finally, the third one is actually from the book on page 619, I believe. So I've gone ahead and drawn up the shape, and it is metric, so you'll want to double click inside the viewport and probably lock it so that you can, I should have locked it first. There we go. so that you can dimension it. So you don't have to worry about drawing it up, but on page 619, at the bottom, here's the shape. So you are to add all your dimensioning in, and of course make them basic when they need to be basic, and then using the information here, create all of your control frames as needed. So it does say the coordinate tolerancing is to be converted to positional tolerancing of equivalent values and reference to datums. So if I'm calling out, let's pick one of these holes. If I'm calling out this hole, for example, it's relative to datum C and relative to datum B and also relative to datum A because it's perpendicular to that, so A, B, C. Then I'll need to make sure that my dimensions come from the bottom, from datum B, and from the left side, from datum C. And then I'm going to take this plus or minus 0.3 and use the Pythagorean theorem to figure out what the diameter of that shape is going to be, and call it out that way instead of calling it out with the tolerance here. So I would just have the 55 in the basic box, and then add the control frame to the hole. I'm sure you guys will have questions as you're going, so go ahead and get started on this 3 and let me know if you have any questions.